Okay, so welcome everyone. So today we have Jerson Caro from Pontificia Universidad Católica de Chile, who will talk about some advances in a conjecture of Watkins. So please, Jerson.
Okay, thank you for the invitation, and also for allowing me to talk about this project. This is the main part of my thesis. Uh, as we talked before, my my PhD advisory is Sector Pastel here in Chile. And okay, I decided to divide this talk in three main parts. The first one would be the preliminaries, and I will fix the notation and give some definitions. The second part would be about uh, this conjecture, Watkins conjecture. And finally, I will talk about the approaches that we gave in the direction to prove this conjecture. So, okay, let me start with the preliminaries, and I will give some modular setting. So, this is a uh, general notions of modularity. So we start with the H, which is the upper half plane. This is the set of complex numbers which have a imaginary positive imaginary part. Also, we define this group, the special linear group, SL2C, which is the matrices with entries, the 2 by 2 matrices with entries in C and with determinant 1. And we know that this group acts on H by this action, the Mobius transformation. We take ABCD and we act on a tau in H. Sorry. In H by this action, A tau plus D over C tau plus D. Okay, and also we define this group is very important, and it's called the congruence group of level n. So we fix a number n, a positive integer n, and it's the subgroup of SL2C, which the C component is congruent to 0 mod n, module n. And okay, since we have an action from SL to C on H, we can also define the same action from gamma 0 n in H, on H. So in particular, we can quotient by this action, and we get a Riemann surface here, and it's called the modular curve of level n. And also we can compactify this Riemann surface, and more or less the construction of that is we take this H star, we take H, the upper half plane, we adjoin the Q and also the infinite point, and we extend the action of gamma 0 n to H star, and we quotient by the same action. So in that case, we have this compactified modular curve, and it's denoted by x0n. And the points that we adjoint, that we joined in x0n, are called the cusps of the modular curve. So, okay, this is the main part of the modular setting. And now I want to define what is a modular form, and I will give you a definition of what is that. And okay, so more or less, what is a modular form is a differential on x0. So we will put some conditions in order to get a differential form, a holomorphic differential form on x0. Yeah. So okay, to begin with, what we do is to compute what are the holomorphic differential forms on y0n. And what is that? Okay, we have this, if we have a function which is holomorphic from H to C, then FCDC is a holomorphic differential on H. And what we need in order to get a differential on y0n is that the action of gamma in gamma 0n is trivial. It's invariant by the action of gamma. So in particular, we can compute, so we need this relation, and if we compute d of gamma tau, we get that relation. Yeah? It's easy, and okay, here is the quotient rule, the derivation, and AD minus BC is the determinant, and since we have this is 1 because the determinant is 1, and so for this reason we have this relation. So what we need in order that FCDC is a differential on y0 is this relation. Yeah, this is the first relation that we need. Okay. Okay. What is the other relation? Well, okay, to get a holomorphic differential form on x0n, we need a holomorphic differential on y0n, but which is also holomorphic at the cusps, the other points that we put in x0n. So what we need here is that f vanish, f must vanish at the cusps. This is the definition of vanishing. The limit when tau goes to R, where R is a cusp. And more or less, why is this condition? Okay, the thing is that this matrix 1101 always belongs in gamma 0 n for every n. Yeah? So in particular, it says that f tau plus 1 is equal to f tau, yeah? Because of the relation before. Okay, and since we have this periodicity, we also have a Fourier expansion for f. And using this Fourier expansion, we can compute f tau d tau. And if we need that it is holomorphic at I infinite, what we need is that A0 is 0, okay? Because otherwise we have a pole in 0, in I infinite. So for this reason, that's the relation that we need. That the limit when tau goes to the cusp, it's 0. Yeah. So in general, what is a cuspidal modular form? It's a function such that FCDC is a holomorphic differential on x0n. Yeah, that's the definition. And this is the three conditions that F has to satisfy. The first one is holomorphic, this relation, and also that vanishes at the cusp. Okay, the thing is that the space of all of those functions is a finite dimension space. Yeah, the dimension is just the genus of x0n. This is the dimension because it's the dimension of the holomorphic differentials. So this is a finite dimension space. Yeah. And we define an all space, which is a subspace of S2C, S2 gamma 0n, and it's the space of all the modular forms. Yeah, the thing is that if M divides N, then we have this inclusion. This inclusion. So in particular, what we need is that we define the all space as the function that has a smaller level. Yeah. And finally, just a definition, I want to define what is a new form. And the thing is that the new forms are in bijection with the elliptic curves defined over Q. And for this reason, I have to define many things. So first, I define the new space. The new space is the orthogonal complement of of this space, the old space, via some inner product that we have on S2 gamma 0n. And a new form is a normalized eigenform. What is a normalized eigenform? Okay, we have that FC is more or less a sum of A n Qn for n bigger than 1, yeah, because A0 is 0. And what is normalized is that A1 is 1. Yeah, that's the definition of normalized. And eigenform is, okay, there are very interesting operators defined over S2 gamma 0, the Hick operators. And okay, an eigenform is a eigenvector of all of those operators. Okay, and okay, a new form is it's a normalized eigenform in the new space. Yeah, in this space, the orthogonal complement of S2 gamma 0. Okay, and finally, uh, for end this first part of the talk, I will define what is an Atkin-Lehner involution. This is another kind of operators on S2 gamma 0, and it's defined as follows. We start with m, positive integer, and we take this q, positive divisor of n, that satisfies this relation. That q and n over q is have the GCD equal to 1. And thanks to this relation, we know that there exists these 4 integers, such that this matrix has determinant q. Yeah, that's the this definition is equivalent to say that the GCD of q squared and n is q. Yeah, that's the same. So in particular, we can find x, y, z, and t. Okay, the thing is that this kind of matrices normalize gamma 0, gamma 0. Yeah? And due to this normalization, we have that we can define an operator from WQ on S2 gamma 0. And the thing is that these actions are involutions. Yeah, when you take the square of all of those is the identity operator. Yeah, and the good thing is that all of those involutions define an abelian group. They commute, and this group is called the group of Atkin-Lehner involutions, and it's denoted by Wn, and has this order 2 to the power omega n, where omega n is the number of distinct primes that divides it. Yeah, the distinct primes that divides. Okay, the thing is that this group is generated by WP to the alpha, where alpha is the biggest power of alpha that divides it. And the other good thing is that if we start with a new form, as what I defined before, this is also an eigenform for WQ, or an eigenvector for WQ. And due to the fact that WQ, the operator is an involution, the eigenvalue should be plus or minus 1. It has to have an order 2. Okay, that's the first part of the talk, more or less a preliminary of what I need to define the invariance that relates this conjecture. What is Watkins conjecture? Okay, the thing is that we have an elliptic curve defined over Q. What you can think about that is you have an expression of this form plus a1 xy plus a2y equal to x to the 3 plus a2 x to the x squared plus a4x plus h. Yeah, you can think an elliptic curve as a zero locus of this function. Yeah. Okay, and over this kind of elliptic curves, when I said define over Q, I mean that AE are in Q. Even better, we can put AE over in C, where integer numbers. Okay. The thing is that over this kind of elliptic curves, we have two interesting invariants. The first one is the Mordell-Weil rank. What is the Mordell-Weil rank? The thing is that Mordell in 1922, he proved that this group, the group of rational points of the curve, of the elliptic curve, is a finally generated group, yeah? And also it's also abelian. And for this reason, we know that this is C to the R, I put E, plus a torsion part. And the torsion part of EQ, it's known. It's known. And the difficult part to compute the structure of the rational points is the rank. Yeah? And compute that number is extremely difficult. And there are many important conjectures about this invariant. So let me show you three of them. Yeah, it's a very famous conjecture, Birchens-Vinetton-Dyer, which says that the rank is equal to the order of vanishing at s equal to 1 of the L function associated to LB. Okay, and okay, it's a $1 million conjecture. Okay, the second important conjecture says that the 50% of the elliptic curves have a rank 0 and the other 50% have a rank 1. And when I said 50%, I mean with density 1/2. Yeah. What I said is that it could be that the number of elliptic curves that have rank at least 2 is infinite, but what I need is that the density is 0. The density of this set is 0. And finally, there is another important conjecture that says that for every elliptic curve, this rank is bounded. So that implies that there exists a constant such that Re is bounded by this constant for every E defined over Q. Yeah. For example, the biggest rank that we know is an elliptic curve that has a rank 28. And many people believe that this constant could be 31, but it's only conjecture. Okay. Questions? Okay. So now I will define the second invariant. It's the modular degree. But to define that, I need to define first what is the conductor of an elliptic curve. Okay, what is the conductor of an elliptic curve? It's a product of power of primes. It's a positive integer, well defined, because what I will say later. But let me define what is this power, EP. Okay, so we have to do some technical algorithm to have a minimal equation for E, but I think that it's not important for this talk. But the thing is that we reduce this equation, module P, then we have a curve defined over FP, yeah, over the finite field with P elements. Okay, and when this reduction is good, so it's non-singular, when the reduction is non-singular, we said that E has good reduction at P. And we define EP as 0, yeah? And almost all the primes reduce well, yeah? And for this reason, EP is equal to 0 almost all cases, almost surely. So in particular, this number is well defined, yeah, because EP is 0 for almost all. We define EP equal to 1 when we have a nodal singularity. And let me draw a picture of that. A nodal singularity is something like that. And here, in this point, we have a singularity, and this singularity has two tangent lines. Okay, it's not a good drawback, but you understand what I yeah, you have two tangents for that point to the elliptic curve. So in this case, we say that the elliptic curve has a multiplicative reduction at p, and we define EP is equal to 1. And in this case, we have two cases, a split multiplicative reduction. And the thing is that the slope of these two elliptic curves, of these two tangents, L1 and L2, are defined by a quadratic equation. So in particular, it could be that these two tangents belongs in FP, the two slopes belongs in FP, or not. And when both tangents are defined over FP, we said that it has a split multiplicative reduction, and otherwise we said that it has a non-split multiplicative reduction. And finally, we have this last case, which is additive reduction. What is additive reduction? Is when the reduction, module P, has a cuspidal singularity. And the draw of a cuspidal singularity is more or less this point here, which has only this tangent line. And in this case, like we said, it has additive reduction. And EP in those cases is more complicated to compute, but is equal to 2 for P bigger than 3. And we use the Thales algorithm to find EP in the case of 2 and 3. I want to say that E2 is between 2 and 8 in this case, and E3 is between 2 and 5 in this case. Okay, so that's where the conductor is of an elliptic curve. So, but we have this theorem. It's a very important theorem in number theory, the modularity theorem, and it says the following. We start with an elliptic curve with conductor n, and we have that there exists a non-constant morphism from x0n, the curve that we defined before, over E. And this morphism is non-constant and is defined over Q. And the modular degree, what I want to say, is the minimum degree among all the modular parametrizations. And what is a modular parametrization? Is this kind of morphism, yeah, from x0n to E. And okay, let me do this technical remark. We can consider an Néron differential of an elliptic curve, and we can take its pullback, and we have this expression for the pullback of the Néron differential. And in this case, we have 2 times pi I times CE, where CE is the Manning constant. It's called the Manning constant. It's hard to prove that it belongs in C. And Fe is a new form with rational Fourier coefficients, integer Fourier coefficients, to be more precise. But yeah, that's the relation between new forms and elliptic curves. Always that we have an elliptic curve, we can define a new form, and the other case is also a construction. If you start with a new form with rational coefficients, you can find an elliptic curve. Okay, and why this invariant is so important? The thing is that why the modular degree is important. It is related with the ABC conjecture. I think one of the most popular conjectures in number theory. And okay, if you can upper bound this modular degree in terms of the conductor, you can prove ABC conjecture. So that's a reason why this number is so important. And now I can state the Watkins conjecture, and Watkins conjecture says the following thing, that it relates the rank and the modular degree, and it says that the rank is at most the two-adic valuation of the modular degree, or equivalently that 2 to the RE divides ME. Now that's the condition. It's the same, and the two-adic valuation is the biggest power of 2 that divides ME. Okay. Questions about this conjecture?
Jerson, can you show once again this V2 ME? What was that? I think I missed.
What is B2? Mu2. This is the two-adic valuation, the biggest power of 2 that divides ME. The classical two-adic valuation.
And the ME was, again, I think...
ME is the modular degree, the minimal degree.
Okay, the minimal. Okay.
Yeah, this is a morphism, morphism of course, so it has a finite degree, and it's the minimum among all of them. Okay, the last part would be the different approaches that are proven, and some of them are proven by us with my thesis advisor. And okay, I will show you some approaches that okay. Sorry. Okay, let's start with this version of Watkins conjecture. Weak Watkins conjecture is the basic case of the Watkins conjecture. So if you see this, this says that when ME is odd, R should be 0. Yeah, that's the thing. And the weak Watkins conjecture says that E satisfies WWC if when E is odd, when ME is odd, then the rank should be 0, or equivalently, when the rank is positive, M should be even. Okay, now in this direction, Domingan and Krishnamurti in 2013 proved this lower bound for ME, for the two-adic valuation of ME. As I said before, WN, omega n, is the number of distinct primes that divides a conductor. This is the group of Atkin-Lehner involutions, and this omega prime, W prime n, is the subgroup of Atkin-Lehner involutions, such that the eigenvalue is 1, yeah, or that WF is equal to F. So I want to say something here is that this index is 0 or 1, yeah. Sorry, is 1 or 2. Sorry. This index is 1 or 2, yeah. 1 or 2. 1 if W prime is equal to W, or 2 if not. Yeah. And finally, we have to rest the two-adic valuation, the dimension as a F2 vector space of the two torsion of the elliptic curve. And I want to say that the two torsion of an elliptic curve is only 3 cases: 0, C mod 2C, or C mod 2C square. Yeah. Oh, yeah. So what I mean is that this is a subgroup of S mod 2C square. So C mod 2C square. Okay. So this is 0, 1, or 2. And this log here is 0 or 1. So I want to point out that the worst case, the worst scenario is when omega n minus 3, yeah, because we have 1 here and 2 here. Yeah? So that's the worst case for this lower bound. And also I want to point out that Kasaliki and Cohen in 2018 proved that every elliptic curve without additive reduction at 2 satisfies that WWC, yeah? When the rank is positive, M is even. Yeah? And I want to do two easy observations of these two theorems. And the first one is that if EQ of, if the rational to torsion is 0, then we have that this is 0. Yeah. So in particular, the worst scenario here is that the quadratic valuation is bigger than Wn minus 1. Yeah. So yeah, nothing to prove here. So in particular, if omega n is bigger than 1, we have that this number always is positive. So yeah. In particular, WWC holds for omega n bigger than 1. So if omega n is equal to 1, then n is a power of a prime. Yeah. And if this prime is not 2, then 2 has good reduction. Yeah. Because the exponent is 0 in this case. So we don't have additive reduction at 2. So 2 proves this case. Yeah. When p is different to 2. And when p is equal to 2, is a power of 2, it's easy to see what are the elliptic curves with this conductor. And we can use, for example, LMFDB to know that, to notice that every of those elliptic curves has a two torsion, rational two torsion, non-trivial rational two torsion. Okay, that's in this direction when we have this two torsion, and the other case when we have a two torsion, then we have that, as I said before, the worst scenario is when Wn minus 3. Yeah, this is the worst thing that can happen. So in particular, the WWC is proven when Wn is bigger than 3. So we only need at most 3 bad primes, and one of them should be 2. Yeah, because 2 covers every other case. So we have 3 primes, and one of those has to be a 2. So we have that there are at most 2 bad primes, 2 odd bad primes. Okay, so that's the last the missing cases for WWC. So yeah, WWC is almost proven, and the missing cases are very small. Okay, so this is the first approach to Watkins conjecture, and now I want to show you another approach, which is using quadratic twists. And what is a quadratic twist? Suppose that you have this model for your curve, y squared equal to a polynomial of degree 3, and you take a number which is different to 0, a fundamental discriminant of q. And what is a fundamental discriminant? It's the discriminant of a quadratic extension of q. And we can do, in this case, a quadratic twist by this d, doing this, taking this equation for E. And it's denoted by ED. And one thing that is important is that these elliptic curves are isomorphic, but over Q square root of D. Yeah. And why is that? Because you can do a change of variables like x to x and y to y over square root of D, and you get an isomorphism. So yeah, they are isomorphic, but over q square root of d, but not over q. They are not isomorphic. Okay. Okay. So, okay, this is the first theorem about the Watkins conjecture. This is the work of Esparza, Lozano, and Pastel in 2020. And they proved that if you start with an elliptic curve with non-trivial rational two torsion, and we put this condition, assume that E has the minimal conductor among all these quadratic twists. I will say something here is that assume that you have that the conductor of this elliptic curve is N. So the conductor of the quadratic twist is more or less d squared times N, more or less. You have to put some conditions in that D and N are relatively prime and something like that, but it's more or less this conductor. So what we do here is to take the elliptic curve with minimal conductor among all its quadratic twists. And then if we put some conditions in D, we need that WD is bigger than this quantity. And this quantity only depends on the original elliptic curve, only depends on E. Yeah, this is the Manning constant that I defined before, and this is the conductor of the original elliptic curve. And when that happens, this quadratic twist satisfies Watkins conjecture. Yeah, and an important corollary of that is that there are infinitely many elliptic curves that satisfies a Watkins conjecture. Yeah, because you can start with an elliptic curve, for example, with conductor of a power of a prime, for example. Then we can compute these numbers, and we can do infinitely many quadratic twists of this curve, and all of them satisfies this conjecture. So yeah, and let me give you more or less the idea of the proof here, and using that the pullback is this quantity, we can integrate both sides, and we get something like that. Yeah, that the two-adic valuation is bigger than this quantity. And the thing is that Delaunay in 2003 and Pal in 2012 gave lower bounds for this quantity, lower bounds for these two quantities. And for example, Delaunay gave that this is at least 3 times omega d minus omega n. And Pal proved that this quantity is bigger than minus 6. So yeah, that's the reason why we have this quantity. And also, we can use the work of Aguirre, Lozano, and Robledo that gave a lower bound for the rank of an elliptic curve. Is 2 times omega d plus omega n. And it is related with what I said before, that the conductor of this elliptic curve, I will denote that by ND, is more or less d squared times n. So this inequality comes from that. And okay, when we put this condition on omega d, we have that this lower bound for the rank, this upper bound for the rank, is less than or equal to this upper bound, lower bound for the two-adic valuation. So in particular, we have that the rank is at most the two-adic valuation of the modular. And I want to say that that all the approaches that are given in this direction is the same. You give an upper bound for the rank and a lower bound for the quadratic valuation of the modular degree, and you compare it. And when you have the inequality, then you have the Watkins conjecture in those cases. Okay, this is this part, and I want to say that in a recent work, I proved that when you start with an elliptic curve with a powerful prime conductor, uh, every quadratic twist of this elliptic curve satisfies Watkins conjecture. So what I prove is that this lower bound can be replaced by 1. So it says that every omega d, every d satisfies that omega d is bigger than 1. So that's the point. Okay, and what is the application of that? The thing is the following. For example, you can start with this. We can start with this elliptic curve, y squared equal to x cubed minus x, and it has conductor 32. And we can do these two quadratic twists. This, for example, has a conductor p squared times a power of 2. And it depends if p is congruent to 1 mod 4 or something like that. And this elliptic curve, sorry. Okay, yeah. This elliptic curve has conductor more or less p squared times q squared times a power of 2. And what this theorem says is that these two elliptic curves satisfy Watkins conjecture, yeah? But in particular, it satisfies WWC, yeah? Satisfies the basic case. But if you see, you notice that this elliptic curve has a rational two torsion, additive reduction at 2, and has one odd bad prime. So in particular, is one of those missing cases in the WWC. And also here I want to give you this other example. You can start with this elliptic curve that has a rank 73, and we can do these two quadratic twist by -4 and -8. And you get these two elliptic curves with these two conductors, and both of them satisfies Watkins conjecture. So this is also another cases when WWC is proven. Okay, okay, that's the other approach that we gave in this direction. And finally, I will show you this last approach, which is for semi-stable elliptic curves. Sorry, for semi-stable elliptic curves. And what is a semi-stable elliptic curve? It's an elliptic curve that has a conductor square free. Or equivalently, that every prime that divides that it's bad has multiplicative reduction. Yeah, that EP is equal to 1 for every P. For every P bad prime. Okay, what we prove is the following. We start with an elliptic curve that is semi-stable and it has this rational two torsion, C mod to C. And okay, if one of these two conditions are satisfied, then Watkins conjecture holds for E. And what is this condition? The first condition is that there are no primes with a split multiplicative reduction. Yeah? And the other is that the number of primes with a non-split multiplicative reduction is odd. Yeah? If one of those conditions are satisfied, then Watkins conjecture holds for E. And I want to point out that that these two conditions happens frequently. And for example, using the database of LMFDB, we can notice that there are 184 isogeny classes of elliptic curves with conductor less than 500. And the theorem is applicable for 99 of those elliptic curves. So yeah, it's applicable more than the half, at least for n less than 500. And I want to give you the idea of the proof, and it's as follows. More or less, the theorem of Dunningham and Krishnamurti says that the two-adic valuation of the modular degree, the same theorem that I stated before, is bigger than omega n minus kappa minus 1. Yeah? This minus 1 comes from that EQ of 2 is equal to C mod 2C. So the dimension as a F2 vector space is 1. And this kappa is defined as follows. Kappa is 0 when there are no primes with a split multiplicative reduction, and kappa is equal to 1 otherwise. Yeah? And okay, what we do is we prove a two descent bound, a bound for the rank using two descent. This follows the idea of Aguirre, Lozano, and Robledo. But the thing is that they prove something similar, but when y squared is equal to a polynomial of degree 3. And the thing is that all of those elliptic curves have a bad reduction at 2, yeah, and additive reduction mod 2. And we need this lower bound for semi-stable elliptic curves. So we don't want additive reduction at any prime. So we have to prove this condition. So okay. The thing is that if this inequality holds, then parity conjecture holds. And this is something like -1 to the rank is equal to some number, which is the root number of the elliptic curve. And yeah, it's related with the number of primes with the split multiplicative reduction. Is -1 to the number of numbers with the split multiplicative reduction plus 1. So that in particular says that the rank and this number, let me put mu plus, the number of primes with the split multiplicative reduction, has opposite parity. Yeah, I will put something like that. Yeah, they have opposite parity. Yeah, that's the thing that parity conjecture says. Okay, okay. So the first thing that you can see is that when there are no primes with the split multiplicative reduction, this bound is omega n minus 1. But the rank is less than or equal to omega n minus 1. So if that happens, Watkins conjecture holds. Yeah. And now we have to prove the second, that if the elliptic curve satisfies the second condition, we have Watkins conjecture. So assume that we have that the number of primes with non-split multiplicative reduction is odd. And we have that Re and omega n have the same parity. And how is that? Because I said before that Re plus m plus is congruent to 1 mod 2. And let me denote by the number of primes with non-split multiplicative reduction, but mu minus. So if we add this number both sides, we get something like RE plus mu minus is congruent to an odd number plus 1 is a positive is an even number, so this is 0 mod 2. But what is mu plus mu minus? It is equal to omega n, yeah, because this is the number of primes. The primes have a split or non-split multiplicative reduction. So that implies that the rank and omega n have the same parity. But the thing is that we have two numbers that have the same parity, and they are not the same number. So the difference should be at least 2. So in those cases, we have that RE is less than or equal to omega n minus 2, and this bound is omega n minus 2. So yeah, that's the proof. Okay, okay, that's what I wanted to say about our approaches in this direction, in this conjecture. But I want to show two different questions, two related questions. And the first one is that you can consider elliptic curves defined over this field, where the function field of with coefficients in FQ, where FQ is a finite field. And we put this condition that it has a split multiplicative reduction at infinity. In this case, we have an analog for the modularity theorem. Yeah, we have an analog, something like N0n goes to E, something like that. But these curves are defined differently. But the thing is that if we have this kind of morphisms, we can define the modular degree. And also, this group is finitely generated. So in particular, we can ask the same question. It is true that the two-adic valuation of the modular degree is bigger than, is at least the rank. And we have some advances in this direction. And the first one is that we prove that if the elliptic curve, there is a family of elliptic curves with unbounded rank in this in the case of FQ over T. And we prove that this family satisfies Watkins conjecture. In particular, this is one thing that we don't have over Q, yeah, because as I said before, it's conjecture that there are not these kind of families with unbounded rank. Okay, the second thing that we prove is that we prove that for semi-stable elliptic curves. What we do is the following: we start with an elliptic curve defined over this field. If we extend the base field, and we think the elliptic curve defined over this field, we have a Watkins conjecture in this case. And finally, we also gave an analog of Sparsa-Lozano-Pastel proof. So using quadratic twist, we prove that there exists a constant for the number of divisors of. Okay, here is a polynomial, but yeah, we prove an analog of this. And the second related question is the following. Suppose that you have an abelian variety which is modular, but modular is a quotient of the Jacobian of a modular curve. It's a quotient of that. And if we have that, we have a definition of modular degree in that case. This is something like that. We have a projection here, and we have the abelian variety here. So we can think the isogeny to pi, and pi composed with pi is multiplication by, sorry, this is multiplication for some integer, and this integer is m alpha. This is the definition of modular degree in this case, and there is an analog for Watkins conjecture in those cases, and it says that 2 to the d times the rank is at most divides the modular degree, or equivalently that d times the rank of this abelian group, finally generated abelian group, is at most the quadratic valuation of the modularity. Okay, yeah, that's what I want to say. Muito obrigado.
Not much from. Okay.
So, are there any questions?
Yunus, if you want to stop.